And then Sean, I'm just going to hit mute on yours, Sean. Sorry about that. I could hear you moving the paper. It wasn't a problem. It was distracting me a little bit. So if you need to speak up, Sean, go ahead and unmute or anything. Sorry if I cut you off there. All right. And then, all right. So let's go ahead. You can, oh, I thought of something. Hey, Trey, I was thinking about making you a co-host. And I think there's a way to do that.
Okay.
Are you okay with that?
Sure.
And then I think what that does is, I believe, if you want to, students, I believe you might now have the option to privately chat with Trey. That way, if you don't want to chat with me, you can chat with Trey and ask your questions. If you want, you could give that a test right now and just check if you're able to chat to Trey or not. I have no idea if that works, but you know, it doesn't bother me. Do whatever you want. But now, Trey, you're also a co-host. If we find that's a useful feature, let me know later. All right. Okay, so let's go ahead and get back into what we were doing last time. We were doing chapter 13, gravity, and we just started. So, ooh, let me get there. Almost there. There we go. Whoops. All right, and so just a quick reminder from where we were. Let's focus on this to get started. Number one, r squared, r hat. There's another way to write that. It's G m1 m2 over r cubed times r vector. And notice that's because r hat by definition is equal to r vector over r the magnitude. Again, the hat is equal to the vector over the magnitude. And so this is another way you'll see it written. That's how we do it in the code. So you have a cubed with the vector, squared with the hat. Notice that down here in energy, there's two things to remember. One is the minus sign. Two is, notice it's to the first power. So it's GMM over R, and it's negative. Energy is negative. It's a little bit uncomfortable at first dealing with the negative energy. But remember, as you go here, let's say you're, whoops. If you're around a planet, let's say that red blob is a planet, right? The closer, whoops, let me get right here. The closer you are to the planet, the smaller your radius. And so this might be, say, -10. And then as you go out, maybe this is -6. As you keep going out, maybe it's -2, -1, etc. And so we see that as you go upwards, delta U is actually positive. Notice it's +4. So, oops, I just wanted to point out, even though you get this minus sign here, changes in energies, delta U's are still going to be positive when you go up, negative when you come down. Nothing wrong there, okay? All right, so there's that. Let's take a look at 13.3. Surprisingly, this one can actually confuse people. It gets uncomfortable when you're first doing it. If we have a mass sitting right here, actually, let me undo that. Let me zoom in a little bit. Oops. All right. And so in this case, imagine that point mass is moving around there, and let's say it gets to this point right here. So there's the point mass. What are the forces acting on it? Gravity. So there's a force due to gravity. The magnitude is G M M over, in this case, I'm going to say little r squared. And notice, because of this weird problem here, little r is in this case capital R plus the altitude. So normally we talk about your altitude for flying objects. So in this case, your altitude is not what you plug in. You got to plug in all of that junk right there. Okay. All right. Now, in this case, it's accelerating towards the center. And I want you to think to yourself, what's the other force acting on this? What's another force that's acting on the satellite there? Excellent. There is no other force. Let's see. Oh, there's a chat there. Oh, yeah, I got you. Oh, okay, I got you. You could chat with anyone anytime. Okay, that's cool. Good. Thank you for letting me know that. And then there's no other force. So this is what confuses people about this one. The free body diagram is this. There's a force due to gravity, and then there's acceleration towards the center, and that's it. So sometimes a free body diagram, remember, the satellite is in free fall. It's trying to orbit the planet, or as it moves, it's falling towards the planet. It just never hits the surface. So you get GMM over R squared. The magnitude should equal. Now here's the other thing. Which mass? In this case, I'm talking about this satellite right here. So that satellite mass, I'll call it this. It's that mass times V squared over R. And again, little r is not the same thing as H. It's not the same thing as big R. Little r is that. All right. So now we see that this drops out. This drops out. Notice the mass of the object itself drops out, but the mass of the planet that's orbiting it does not. If you've ever wondered how they figure out the mass of a planet, now you know. You could look at a moon or something that's orbiting that planet. If you can find something that orbits the planet, the speed of the orbiting body relates to the mass of the planet and, of course, the radius of the orbit. This is a huge deal. If you know the speed or the period of the orbit, and you know the radius, you can get the mass of the planet. All right, so let's go in there and let's get out of here. Let's go look at the solution, see if there's anything else. There we go. And okay, yeah, you're okay, whatever. So there's the velocity from solving that one. And then, okay, great. Did somewhere, notice if you need to get the period, that's distance over time. So that's going to be 2 pi times the radius, which is r plus h. And so if you get the velocity, you could rearrange that and solve this for period. And notice it's some constant times the radius to the 3/2 power. That's one of Kepler's laws. And notice this, we can get the kinetic energy if we need it. That's 1/2 mv squared. You can get the potential energy. That's really easy. The GMM over R plus H with the negative sign. And notice that the kinetic energy is actually the opposite of the potential energy divided by 2. So the total energy is actually half of the gravitational energy. So again, this with the minus sign is gravitational, and then this half comes from this unusual, for a circular orbit, the fact that they're related in this unusual way. I'm going to pause there and see if there's any questions. I don't know if I'm going too fast or not, but let's take a look. Normally I do all this work on the board, so hopefully there's that. Is that making sense, everybody? If so, just let me know. I'm just pausing for a second. That's 13.3. Do you know what you're missing, Ryan, or no? Or are you thinking? Oh, I'm not. I'm not. You could, but I'm not. So to be clear, let's take a look at the questions again. I kind of skimmed through that awfully fast. So let's go look at the questions. So notice the first one is figure out the energy. And then, so notice here's the energy problem. And then I had you do the force problem. And now throughout you see that if you do all this problem, I should have put A, C, and D all together and then put part B later. Okay. So my apologies there. And so, but we do see this unusual relationship being formed. Whoops, where is it? Right here. We do see that I know the potential energy. And if I know it's in a circular orbit, by doing the free body diagram, we discover this interesting result. You could actually say, well, I could figure out the velocity by doing this and setting these two things equal. I did it the other way. What I did is I did the free body diagram and then showed that the kinetic energy happens to be that. So they happen to be related, but I wasn't using the relationship. Is that good on that? Yeah, and so if you have a circular orbit, we can now use circular orbits are special. Elliptical, it's not going to work the same way. But now we could use this unusual result. You could say for any circular orbit, K equals negative 1/2 U. And so not 1/2, K equals negative U. This looks a little cleaner. So K is equal to negative U/2, and then you could actually solve for the speed for circular orbits. Okay, other questions? Interesting to note, you could actually use that in your codes, and you could do your Euler-Chroma relation using a coincidence, Sam. It's a coincidence. There's I think it's called the Virial theorem in mathematics, which turns out for circular orbits, it obeys this. But typically the reasoning is this. So that's kind of the logic in my brain. Whoops, you do an FBD, you solve that for V, and then by chance, it just so happens for circular orbits only, we get this weird result. And it's because we do know U is negative GMM/R. So it's just coincidence that happens. Nothing special there. If you're a physics major, you'll learn about virial theorems and when they apply later, much later, like grad school usually, or maybe senior year. Is that good enough, Sam? All right, right. All right. I'm going to go ahead and jump back in and take a look at the next problems. All right. And keep the questions coming on chat or speak up, whatever you want to do. Hey, guess what we're doing in lab this week? All right. Got that. 13.3.5. We addressed that last time, but you should reread that again. Okay. All right. So this, let's take a look at this one. Oops. Sorry. Here we go. All right. So it's important that you learn how to do these problems right, because this is the first part of Physics 163. So if you're tired of this class and you want to get lazy, this is not the time. All right. This stuff will directly benefit you in your next semester. So if nothing else, it will help you get rid of me in your life, which is a good thing. All right. So let's take a look here. We've got 3-point masses. We're looking at them from above. So, okay, we're looking from above. These are sitting on a table. Technically, they are attracted to each other. It's just the gravitational force is so weak. We'll see that in this part. So, right, in part C, we'll discuss why they aren't moving, even though they're attracted to each other, okay? But for now, M2 is bigger than M1. Let's see. And I'm going to make this a little bit bigger. so I can draw on it. The idea here is red for 2 on 3 and green for 1 on 3. All right. So number 1 is going to attract. So that's the force vector of 1 on 3. I think most of you have no trouble with that. And then this other one, that's going to be attracted to it. So that's the force of 2 on 3. All right. And so in this case, you could take your guess which one. This has twice the mass. This is 2m, whereas this one, I believe, is only just m. And so I would guess that the 2m is only a little bit farther away, but has twice as much mass. I would think it actually exerts a slightly larger force, but I could be wrong. I haven't done the math in a while, so I may be wrong. Somebody else might argue m should exert more force because it's significantly closer and it's radius squared. That's a pretty good argument too. I haven't done the math, right? This one is 4 units, I think. Let me just double check here. 40 centimeters. Okay. Whoops. All right. So in this case, this distance is 40 centimeters, whereas the red distance, if this is 30, right? If that's 30 centimeters, then this one here is probably going to be 50 centimeters, 3, 4, 5 right triangle. Okay. And so just based on that, this one's twice the mass and this one's only 25% more the distance. So 25% more squared is going to be a lot less than doubling the mass. So I think this is probably good. Let's go ahead and look at the solution and go through this together. Okay. And my apologies if I'm going too fast. I have no idea. So I think I did a detailed solution for that one. All right. So it looks like if we just look at the numbers for this one, okay, so we see that there's a couple different styles here, and I want to go into this. So, oh boy. All right, let's go take our time going through this solution. This is very dense. So notice style 1 is going to split things into components using SOHCAHTOA. All right. And then style 2 is going to use the unit vectors. I'll be honest with you, for a lot of you, this way is going to feel much, much easier. So if you want to do that right now, that's fine. You might be saying, why would I ever need this? If you have a 3D problem, this is the only way to go. So you really want to learn both. Plus, I know in Physics 163, you need to know style 2, and you are tested on style 2. So I would take the time to learn both methods, even though it may seem like you just want to get this over with. Remember, you do have a follow-up course, almost every one of you. Okay, so let me zoom out just a little bit now. All right, so notice what I do here on the side. This is important. I do 2 pictures. One picture is strictly lengths and angles. Again, one picture, just lengths and angles. From this, I'm pretty sure you could figure out theta, but notice what I did right here. I didn't even bother to get theta. If you don't know a 3, 4, 5 triangle already, you probably have it memorized. This particular one is 53.1, or the other one's 36.9. So this angle is 53.1, just if you have it memorized, and this is 36.9. But notice you could just get sine and cosine. So now anywhere I get cosine, I didn't have to take the time figuring out the angle. I just got the sine and cosine of the angle. Now in this particular case, let's go through the green one. The green one, how did I get this thing? I just did G, M1, M2, or wait, M3, because we're doing M3, divided by radius 1, 3 squared. That gives you the magnitude. So if you're wondering how I got the magnitude, I did this. If you're wondering about the red magnitude, how did I get this? That's going to be G M2 M3 over radius 2, 3 squared. I would take the time to practice dealing with these things, because one of the things you find out in this problem, centimeters don't work. This is 0.500 meters. So remember, G is 6.67 times 10 to the negative 11th. And then it's meters squared times a Newton over kilograms squared. And so because G has units of meters in it, I need units of meters right there. So that's a couple of things that you need to watch out for. Okay? And then when you do that, it's exactly the same as every other vector problem. Now I know the I hat and J hat crap. You might be saying, well, wait a minute, all of this one's in the J hat because it's straight up, right? If it's straight up right here, if it's straight up, there's 0 in the I hat and the full magnitude that way. All right. And now the red one, it looks like you're going to get a cosine theta, right, in the I hat plus a sine theta in the J hat. And so that's why there's this number right here. Oh, and it's in the negative I hat. Negative I hat. Okay. And then you could plug in this 0.6. I got this one here in the J hat. I could plug in that 0.8. And when you do that, you then add the I's to the I's and the J's to the J's. Wait a minute. Is that a typo right there? Is that supposed to be a J hat? Probably. I'll write that down. That's supposed to be a J hat. Something. Solution. What is this? 13.5. Sorry about that. Another one of those ones that we usually do on the board, so I don't usually look at the solution. All right. I want to pause for a second and make sure everybody's okay with that. Looks pretty good. All right. Let's get back in there. My apologies if I'm going too fast. It's so hard to read people in this way, but style 2, I wanted to focus a little bit on. We get the magnitude the same way, okay? And now, in this case, look what I'm doing here. R1 to 3 hat. That's from 1 to 3. Now look carefully. That minus sign might be pissing you off, right? Look, take the time to actually understand this. This minus sign is correct. If I go from 1 to 3, it's in the negative J hat. And so this is 40 centimeters, negative J hat, right? The magnitude is 40 centimeters, so that's how I get this. Look at R2 to 3, okay? R2 to 3. I go, let's see, 30 in the I, positive, minus 40 in the J. So that's where I get this one. And notice, it's just the same thing as doing SOHCAHTOA. Look, can you see that right there? It's exactly the same. The one part that's weird about this is when you look down in here, notice there's a minus sign in the definition of the force formula that flips it. So that's how this negative J hat becomes a positive J hat, which is the correct direction for the force. I'm going to say that again. This negative j hat gets multiplied by a minus sign in the definition of the force, which then makes the force point the right way. So if you trust the math, it works out the same thing as SOHCAHTOA. Again, why would we waste our time? It's because style 2 works in 3D. Style 1 does not. Style 2 also works in Python and in some other coding language. So this works in 3D and it also works in coding. So there's a reason you would want to do it, and that's the reason. That said, if you can answer the test question with style 1, do it. It's faster, slightly, for you guys, because you're really good at style 1 right now. That said, make sure you learn style 2. I'm going to clear all that. So, and notice here, how did you get this? That's just x squared plus y squared square root. And so how, oh, let's scroll down just a little bit. So notice you could get these angles right here. I'm looking at this picture right here. Looking at that picture. And so I did the parallelogram rule there. And so it looks like I did 20.8 degrees west of north. Somebody else might say, what's that going to be? 69.2 degrees. Is that right? 69.2 degrees north of west would also be correct. Okay. I guess you could say 110 degrees from the positive x-axis, or 111 degrees or something like that. Hey, it looks like this is probably important to mention right here, this giant mega font. This is not true. Okay, I've seen this on every final exam that I stick, a gravity question, which is every final exam in this course. Every time somebody does this move, and I just like, dude, you're killing me. Okay, so this is wrong. You cannot get the I hat components by just taking the I hat part of the distance. This doesn't work. You can't get the J hat part by just taking the J hat part of the distance. This doesn't work. Okay, cannot emphasize that enough. Notice, how do you get it? Let's go back to the definition here. It's from this. So you don't get, you have to do the full distance and the full R hat vector, or SOHCAHTOA, and split it up on the way. Okay, they're the same thing. So this R hat vector is a fancy way of doing SOHCAHTOA that's also valid in 3D. All right. Let me get back down here. And let's go back and see if there's anything else in that question worth knowing. Okay, so we kind of worked this out. Whoops, we did this. Okay, now I hope you noticed something in those magnitudes. If I go back to them, look at these magnitudes. Nanonewtons. Nanonewtons. We're talking about masses that are several pounds. These are 1 kilogram and 2 kilograms and 3 kilograms, right? So 1 kilogram near Earth is equivalent to about 2.5 pounds, 2.2 pounds. So we got a 2-pound mass, a 4-pound mass, and maybe a 7-pound mass, somewhere in there. 2 pounds, 4.5 pounds, 7 pounds, something like that. And so these things are only producing nanonewton forces. By, by comparison, mg is 10 newtons. All right. So you got 10 newtons, 20 newtons, and 30 newtons is the mass, is the weight due to Earth. These gravitational forces due to the other point masses are completely negligible. Completely negligible. So even though you're attracting every single object in the universe, that's why we're not suddenly thrown towards them. It takes a planet-sized mass. And if you're trying to remember where that comes from, it's from big G being 10 to the minus 11. Obviously, there's 6.67, okay? It's this 10 to the minus 11, which means only until you have 1 billion kilograms is this going to be appreciable at any size. All right. And then one more piece here. I wanted to make sure. I believe this question also asks us, so it's about 1 billion times larger, something like that. We'll look at the numbers. And then the gravitational potential energy. All right. You might be tired. I know you're tired. This is something good. Let's make sure we get this. We have a group of masses. I hope you remember this from last time. I glossed over it, but there's 3 masses. That means there's 3 possible pairs. 1 with 2, that's a pair. 1 with 3, that's 2 pairs. And then 2 with 3, that's 3 pairs. The way I keep track of this is as follows. U total, just trust me. If you can hear me, I'll go through this twice to make sure in case my computer's lagging. Start with number 1. Make every possible pair with object 1. 1 can go with 2. Next, is there anything else 1 can go with? 1 can go with 3. Okay, is there anything else 1 can go with? No, I'm done. Let's go to the next one. Start with object 2. Okay, check with object 2. 2 can go with 1. Already got it. So the next is 2 with 3. Fine. Now I'll add in. I'll check if that's all of them. And then 3. Well, I already did 3 with 1. I already did 3 with 2. Oh, so I don't need it. I'm going to get rid of that one. Got it? And so that's how you can make sure you hit all the pairs. Start with 1, go through every option. And, you know, this is going to kill me, so I'm going to go to the chat. So if you had 4 masses, this is what it would look like. You'd have U12 plus U13 plus U14. And then you keep adding. Now I go to the 2s. U23 plus U24. And now I go to the 3s. Plus U, I already did 3 with 1. I already did 3 with 2. So now I got U34, and that's it. And so they always start forming these triangles if you're writing them out. You can see that there's 3, and then 2, and then 1. So they'll always form that pattern, right? In this case, we had 3. So I started off with, I had 2, and then went 1, and then I run out. Okay, so that's how you figure out the total potential energy. Let's go look at the formula and see if I did anything clever there or worth noting. And then I'll get to the chat in just a minute. Trey's on it if not. Okay, so let's take a look at, so there it is. Don't overthink it. It's this one, plus this one, plus this one. Notice big G factors out. That's 1 times 2. That's how I got the 2. And then 1 times 3 is going to be 3. And then what is this one? 2 times 3, that's a 6. And then each one has a different distance between them. So make sure you use the correct distance between them. And then I added it all up, did the math, and I got that number. So make sure you actually punch these in. And notice, check this out. Look at this. I didn't use centimeters. Okay, I used meters because, again, big G has units of meters. Oh, yeah, there we go. There's a pretty cool way you could do this in the lab. I actually had some Hancock students build a device to measure big G. It's really hard. If you walked into the room, you had to walk really slow. It was like a bad Tom Cruise scene, because if you walked too quickly, the wind would dwarf the gravitational force. So if you want to measure this, yeah, it's pretty hard. Let's stop the share and see. Okay, so yeah, the Cavendish experiment, usually you put up wind blockers, but they have to be really light. And anyways, you can actually notice this. I think we used some 40-pound lead weights or something. All right. All right. Any questions on that one? We see the energy is a lot easier to compute, but force is sometimes needed. And so we have to know how to do both of those. We see that there's the R vector and the R cubed, or the R hat and R squared. And we see that you could either do SOHCAHTOA for a 2D problem or the negative R hat crap for a 3D problem. Should we try another one? Let's go for it. And apologies if you're bored out of your minds, but we only have a couple weeks to go, 2 weeks, in fact. So let's do it. All right, let's take a look at this next one. All right. Oh, question there. Let's see if it's got a, let's see, where is that? Probably not in this class, but probably in your next class. So it's worth it to take the time to learn the 3D. Usually I don't put 3D in Physics 161. I do more 3D in Physics 163. Is that good, Ryan? Cool. Yep. So you should definitely practice it just so 163 doesn't kick your butt. All right. All right. Question? All right. So in this case, notice there's a lot of these problems where it has plots. I am telling you right now, you will learn this at a much deeper level if you make the plots. You will be better at Physics 163 if you make the plots. And in general, you'll be a much more capable, competent scientist if you practice making plots all the time. Yeah, it's a nuisance. But to be very clear, at the minimum, I expect you to actually make these plots. I'm not going to grade it. I'm not going to turn it in. But if you don't get used to making these, you don't learn the tricks of dealing with scientific notation and units in plotting. Okay, we talked about that last time. I cannot emphasize it enough. At least do those 2 plots. And once you get used to it, these ones get pretty easy. Okay, so here we go. We're going to, oh, okay. Watch out. So the outer 2 masses are held in place. The middle mass is free to move left or right. Look at these bounds. So that means we're going all the way out to about here, right? Isn't that 2D? And all the way over to about here, which is negative 2D. So what we're curious about is what happens to this middle mass. And notice there's 3 regions. There's way over here, there's in between, and then there's way over here. The potential energy, it gets a little bit sneaky. So let's go in there and actually look at this one. And I think you might be thinking to yourself, this problem it's pretty simple. I don't need vectors. Everything's either plus or minus in the I hat. And you're right for the force. However, there are times, and this is one of them, where learning the 3D technique actually simplifies the math. And let's go look at this one. So, yeah. Okay. So notice this absolute value has to pop up in your equation. And you might notice what's going on there. So again, every term. So to be clear here, we're going to have U total. Because we have 3 masses, there's going to be a 1, 2, a 1, 3, and a 2, 3, right? So there's 3 terms with 3 masses, 6 terms with 4 masses. And those are, I never go above 4 for a test question. So, all right. So notice in this case, every term has a big M because let's see here. There's always, there was a big mass here, a big mass here, and then a little mass right here. So we said this distance was x. And so you might be saying, oh, isn't this distance just d minus x? And you'd be right. And isn't this distance here d plus x? Yeah, usually, most of the time. But watch out. We got to read carefully. Okay. Let me go over to the other problem really quick. Let's see. Does it say what x is? do you agree that according to this picture, X could be positive or negative? X could be positive or negative. So let's go back to the solutions here. X could be positive or negative, and that's why we might need to do these absolute values. Let's think about this. This is the kind of stuff that shows up. If X is negative, if I was over here, this would be X is less than 0, right? It would be negative. If I do D minus a negative number, it's going to give me this huge thing here. So this, what I just told you, will also work for negative values of X. Now, what about this one? If I said D plus a negative number, it would be less than D. So that one's also working. But what if it's way over here? Right? We got to think, what if it's way over here for X? Well, now we have to be a little
Right then. So, there's the features. Cool. Let me kind of quickly redraw this. I can't see anything, so if you guys are saying anything, I don't know how he does it. It's a Christmas miracle. So here's mass 1, mass 2, and then the variable mass over here in the center again. So what he was doing before, obviously we saw that it can, oh, there's chat. Cool. Yeah, fuck it. Language, oops. I will try it. I will attempt. So let's see. So obviously all the things that we did before work as long as X is been within the bounds of D. So if X is from here to here, we can use this function, because obviously if it's D minus X, then it works here, or if it's negative, then it's still fine. It'd just be this region or this region. Oh, maybe. Okay, we'll see. We'll continue. Anyways, moving on. I hope everybody can hear me. I'm pretty sure it's enabled. But anyways, so if, okay, cool. However, if X is in these bounds out here, and you do D minus X, you end up with a smaller number that would correspond with X only being around here. Because if you did like D minus...
Sorry about that. I don't know what happened. It crashed, so I went out to check my kids, see if they're doing something weird, but no, it's just, I don't know what it is.
It's fine.
Oh, Trey, thanks for I guess it was good I made you co-host, huh?
Yeah.
Go ahead and finish whatever you're saying, Trey, all right?
Sure, okay. I'm pretty sure I was seeing where it was going with this next function. So I was just kind of trying to predict that part. So if X is greater than D, or I guess absolute value of X is greater than D, if you try and do D minus X for this distance here, you would end up only with this distance being represented. And that's an issue because that only corresponds to this. So if you square it and take the square root of it, now you get the full value, this whole thing, versus it just this portion. So that's what this next part is.
Excellent. Right on. Cool. Should I try and take over again?
Yes.
Okay, cool. Thanks, Trey. Let's see. let's see if I can get back to where we were. All right. So, whoops, we were this one. All right. And so that was really cool. So we could see that this is a fancy way of calculating the R distance. And I'll show you more about that in just a second. And then, all right, part B. So let's review part. Okay, so that's the energy. The same thing. So this explains why you need the absolute values of this for whether you're outside the region where the two masses are. So I'm going to leave that and hope that's good. I can go over it again if it lagged out and screwed things up. Now check this out. When I did this one, I got myself. I tricked myself. So if you're one of those students that's like mad when I trick you, I tricked myself too. So look at this one. I just assumed it was this. Here's the distance, right? And here's this distance. It turns out that's not correct. I made the plots, and this is what makes me such a plot kind of guy now. I didn't figure out my mistake until I made the plots and say, wait a minute, these don't make any sense. And so when you do this one, it doesn't flip it. So blah, 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 blah. It looks like you could do this and you could do each three cases. And so let me show you what I mean by that by going over to the other picture. All right. So what you could do is you could start by considering this case. In this case, I would say this mass attracts that way and this mass attracts that way. And so I would take force. If I label these, let's call this 1 and 2. So if I had the force of 1 on 3, this one here is 3. And this would be the force of 2 on 3. You'd see that you should subtract them. The difference gives you the force magnitude. If you're out here, notice they're both going to the left, right? And so there you would need to add them. And if you're sitting over here, they're both going to the right. And that's the issue, is sometimes they add together and sometimes they subtract from each other. So when you're outside of here, you need to add the two forces together and put a negative I hat on it. When you're over here, you add the two forces and put a positive I hat on it. And when you're in between, this one gets a plus and this one gets a minus. Fairly complicated for a one-dimensional problem. Okay. And let's check the chat. All right, so there we go. All right, that's good. And now I want to show you something that I discovered afterwards that I'm like, you know what? Why don't I just do full 3D for everything? And check this out. If we just do full 3D on this problem, this is how you would do it. And it's actually easier once you get used to it. And so notice what I did is I said R 1 to 3 is this. Take a minute to kind of think of that. This is the position of mass 3. This position of mass. Oh, shoot. Okay. Okay, good. I named them the same. Just checking. So 3 is our, oh, no, I didn't. Oh, crap. I got to make sure I named these. I'm losing it. I think what I did, sorry, I used a different numbering system. I believe this one's 2. And it looks like that one is number 3. So this one looks like 3. And isn't this a capital M? And then this one, oh shit. That's from, this tells you how important this stuff is. I copied this from my E&M solutions. Do you see that? The same math, this should be G, M, and then M, I think. Something like that. Oh my gosh, so bad. All right. I got some work to do on this solution here. All right, so this is number 1 though. The idea here is if I go from 1 to 3, I take the position of 3 minus the position of 1, and I get this result. Notice that naturally gives me this result for the distance between them, which gives me the absolute value without having to think about it. And this is valid in all three regions. I can come over and do the, oh geez, anyways, I could do the same thing for this other force and do it all with this style. And if you do all of it in this style and get used to it, this one-dimensional problem has one region to worry about instead of three. That's what I was trying to point out here. If you use this style with using the R hats, there's basically only one region and the problem does it all itself in one step, as opposed to having to do this thinking, as opposed to having to do this crap and think about the three cases. So you could think about the three cases. It's not that bad. We did that. Or you could just use style 2 and let the math do the thinking for you. I kind of like that personally. All right. So let me get that chat question there. Yep. Right. Yeah, it's okay. It's just one of those days, I guess. All right. Which problem is this? 13.6. It does show you that this stuff is used in Physics 163. It's the same exact problems. This whole chapter, you're going to do it all again, but it's going to be charges. There is one significant difference. Charges can be positive or negative. Charges adds another level of confusion where the forces could be away from each other or attractive. And so it's important that you really nail down this stuff with gravity. That way you can deal with this style here. Can you please shut the door? Thank you. That was my kids coming into class. All right, there we go. Holy cow. What a crazy day. All right. I don't care, man. I just want you to get it done. Yep. I just want you to learn some physics. And so I think you want to learn both. And by doing the coding, you'll get better at doing the R hats. Is that good, man? All right, cool. All right. So, man, a lot happened during that problem. My computer crashed and then everything. So, is it okay to go on to the next problem, or do you guys need me to redo anything from that? Or are you guys ready for the next problem? I have no idea how bad that went. Okay. All right. I'll just take Eston is making the decision. All right. That's good. All right, cool. A couple of others there. All right. So my apologies. Thank goodness for the solution manual, right? Let's take a look at 13.7 here. We're definitely finishing this chapter tonight, by the way. All right. All right. So this is a really good page, by the way. If you could do this page, you're in good shape for the test. Notice it's all 2D, but most of the questions that you're going to encounter on this page, one of them is going to look very similar to what your exam question is, almost certainly. Actually, these two pages, right? Yeah. So this has got the circular orbit, right, which is an important force question. This has got three masses just at some random spots. This has got three masses in a line. Here's a triangle geometry, and here's the square geometry. So this pretty much looks, one of these questions is going to be pretty similar to your final exam question about gravity. All right. I don't know which one, and I'll give you a couple more to practice after these. But okay, let's learn about the tricks of the triangle geometry. Equilateral triangles come up in a lot of interesting civil engineering applications, or just lots of physics applications as well. So mechanical engineers, it's very common to deal with equilateral triangles. So notice this first two bullets is make sure you can understand the geometry of the equilateral triangle. And once you get parts A and B, you might want to memorize those, or for your final exam, I'm going to let you make a one page of notes. Maybe this would be one of the items you add to that page of notes. Okay. One more. All right. So in this case, let's go two more. Let's make that a little bigger so I can label it. All right. In this case, this is how I remember it. You could do whatever you want. You could do straight memory tricks, but I like to do this. This is a 60-degree angle, right? If that's a 60-degree angle, and this is the center of the triangle, this is the center of the triangle, take a guess what angle that is. Hopefully you said 30. All right. And so now what you could do is you can actually use this 60-degree angle. And so we could relate, it looks like sine of 60 is H over S. So that means H is S sine 60. This comes up, so we got to know it. All right. That's how you can get the height of the triangle. Are there other ways? You bet. Memorization is an easy one. All right. But now what about this side? How do we get this side? Well, I know this side is S over 2. Agreed? Because this is cut in half. So this part right here is S over 2. So if I know that, I could use, it looks like cosine. Is going to be what? S over 2 divided by D. And now notice that if we solve this for S, you got to do a little bit of math and flip it around. Are there other ways to do that? You bet. But that's you there. And I see there's some chat. I'll help in just a minute, or hopefully Trey's on it. This is another one right here that's commonly figured out. Notice you could relate these with a tangent of 30. So if you're trying to remember the equilateral triangle, my advice to you is don't remember the equilateral triangle, except for the fact that you know a 60-degree angle, a 30-degree angle, and you know how to use SOHCAHTOA. Now, it turns out y is equal to 1/3 of h. That's another cool thing that you can memorize. If you want to know where the center of a triangle is, y is 1/3 of h. Whoops. So this is a cool fact if you want to memorize it. That's some geometry right there. Obviously here, if you're going to solve for this one, d has got to be rearranged. So what is it? D is equal to s over 2 cos 30, I think. So d comes up, cosine comes down. It's good. Okay, so there's that weird 2 in there. That's what sometimes gets people. I'm going to check the chat, just see if there's anything I needed help with. Let's see here. It said, oh, yeah, Phil, I'm sorry. I guess I just assumed it's a perpendicular bisector. And since all the masses are equal, I assume it's going to be pulling everything straight towards the center of the triangle. So, yep. That's right. Yep, everything. Yep. So, okay, yeah, sorry. I was too focused on the geometry there for a minute. And so, yes, I absolutely was assuming this was a perpendicular bisector. The problem said it was equilateral, and then I dropped that line straight down, and I'm just figuring out H and D. So I've got those. So again, when you're doing this one, don't remember anything other than this is 30 degrees. This is 60, and you can do SOHCAHTOA, okay? So that's how I would recommend analyzing an equilateral triangle, so you don't have to memorize a lot of crap. You already have SOHCAHTOA memorized, and you know an equilateral has 60 degrees. So let's go over and read the question now. Okay, so now, and so I was first just analyzing the geometry. That's all we did. Hopefully that makes some sense. If I want the gravitational potential energy, there's going to be three terms. We see this happening over and over and over again. U12, U13, U3. So that's pretty straightforward. And actually, look at this one. They're all distance s away from each other. So that's just 3 times gm squared over s. Let's go look at that one with a minus sign. Blah, 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 blah. Look at those cool plots. Make sure you do them if you have the time. All right. So we're up to 13.7. So there's that. There's D. So notice we get these results. After that, it turns out, okay. Look at this. They're all the same distance apart. They all have the same masses. So this is a trick I'll sometimes do on test questions is I'll make all the masses a multiple of m. That way you could get some simplified math. All right. If we put a fourth one at the center, then it gets tricky, right? It's going to add in all these other pairs. 4 with 1, 4 with 2, and 4 with 3. And so it would be to add in 3 of these. But because D is this size, again, I have no idea how laggy my computer is. So if we put a fourth mass here in the center, we have to add in these 3 terms because there's a distance here, D, D, and D. But because of this, I can get this other result right here, which gives me this right there. Oh, and the change, I see. Let me read the question carefully. Let's go read that question. Okay, so now you see a way I might trip you up. There's a difference between potential energy and change in potential energy. So in this problem, I asked for the change, and that's why it wasn't just doing this thing. So if I go back there, this is the initial energy, the final energy right there. So if I subtract off the initial, all I'm left with are these terms, which gives me this, which gives me that, which gives me this. All right. And let's go back and take a look at this. Determine the work done by gravity as the fourth mass is brought in. This is a question I'm trying to see if you remember this weird fact. Work is equal to negative delta U. That was one of the ways that we defined potential energy. That was the way, right? So if work is negative delta U, and we just found delta U, that way is actually pretty easy. All right. Now check this one out. So this goes to Phil's question. He was wondering why I was doing all this crap. It was because I knew at part F I was going to ask this question. Net gravitational force on this mass at the center. So think to yourself, I could get the force due to this one, the force due to this one, and the force due to that one. This one looks like crap, so I'm going to redo it. Hopefully you see right away, net force is 0. So knowing symmetry is a good trick. Knowing symmetry is a good trick. Now I want to get to this last part. What if it's halfway between? If it's halfway between right here, hopefully you see that the 1 and the 3 will cancel out. So all I have to do is figure out this. And I know what H is from this part. From part A, I know what H is. So it's going to be G m squared, because there's both mass m, over H squared. That's the magnitude. And then the direction from the picture is plus j hat. So with this problem, we see that symmetry can dramatically reduce your work. That was the point of this problem, was to show you that, oh my gosh, it looks like it's going to be horrible, equilateral triangles, angles everywhere. But a lot of times symmetry will reduce your workload. And this is sometimes true on exam questions as well. All right. Let me give you another example, all right? So let me just make one up on the fly here. Actually, let me see if I've got it on the next page. Actually, look at 13.14. It's page 122. I'll bring it up as well. Whoops. There we go, this one. If I'm gonna make this picture a little bit bigger. All right, so in this case, check this one out. This one is going to be attracted to there, right? It's also going to be attracted to there. Notice, let me get a, there's an X component and an X component. So for this problem, this is again 13.14, page 122. Notice it's actually a lot easier. You could just say, by symmetry, rather than doing all the work, it would equal twice the X component in the negative I hat of so if this is force 1, all you have to do is get the X component, double it, and then say the force is in the negative I hat. And that gets you the net force. That's why you want to learn how to use symmetry. You want to learn symmetry because in problems like this one, it dramatically reduces your workload. You only need to figure out force 1 and then get the X component of it, done. All right, that's why you learn symmetry. All right, so that was just to motivate you to care about the symmetry. Look at problem 13.20 right now. Look at 13.20 on the next page. Right? It's in 3 dimensions. It looks gnarly. I'm going to show you the solution. Then after this one, we're going to take a break, okay? So where is it? There it is. So in this case, oh my gosh, am I not sharing my screen? Hold on, there we go. I thought my Zoom just crapped out again. I was about to lose it. All right, sorry about that. Look at this one now, right? This one is a very complicated force. There's going to be a force attracting it this way in 3 dimensions. Notice it's got an X component, a Y component, and a Z component. This is really complicated, but because of the symmetry, notice this one's going to go this way, and up. We see that every single one is going to have only an I hat part survive. So the trick with this one is, rather than do all this, you first just figure out the I hat component of the first one, multiply it by 4, done. And I'll show you that in the solutions, okay? So we see that if we look at the solutions for this one, right? Here I write the vector in 3D. So I'm looking at 13.20. It's not that scary, right? Let's just take our time and get this one problem right, and you'll realize, oh, I can do this if I'm patient with myself, all right? So here we go. It goes, and I need to split the screen here. All right, so take a look, and if I could, I need to make this one a little bigger. All right. Negative s over 2 in the I hat. That's right here. The square is side s, so that's s over 2. Okay. Oh, shit. Look, we're going from 1 to 5. So let me clear that out. S over 2. Okay. And now it's going y in the j hat, right? That's y in the j hat. And then, oh, we better add in that. That's going to be s over 2 negative k hat. And so if you look at this one, this purple vector from here to here is the sum of the blue, the green, and the red. So we get negative s over 2. And so if you can do that, we're good to go. Now I did a little bit of math tricks. This looks sneaky. Oh, whoops. Right? You're going to get an s over 2 squared plus another, s over 2 quantity squared plus a y squared, right? Square root. And then notice these two, when you add them up, there's 2 of them. That's why I get an s squared on top, but I don't get 2 squared on bottom. I only get a 2. And here's my vector, my hat vector. So then I plug it into the force equation, and every problem looks the same if you get used to this style. It's just, it doesn't matter whether there's numbers, letters, or whatever. And then looks like I got to hit, there's a weird space bar issue or something, or a font size I got to fix up there, but whatever. Now I just plug it in. There's the magnitude. This is minus r hat. That's minus r hat. I'm not thinking too much. I'm just doing what the math tells me. Notice this squared and this half cancel out. I get this crap. There's the force. It wasn't that bad. It just take a deep breath and start grinding. Now notice this 1/2, and then I've got this canceling out. I get a 3/2. It's because this is to the 1, and this is to the 1/2. 1 plus 1/2 is 3/2. Again, just trying to emphasize that a different way. These drop out, and this is to the 1. Well, that's also the same thing as saying it to the halves, right? So 2/2 plus 1/2 gives me 3/2. That's where that comes from. And now, if I want to get the net force, it's a piece of cake. Oh, I see. In this case, it's a j hat term, right? So because this one's in the y direction, I'm going to pick off the j hat term. So I grab the j hat term and multiply it by 4. And that's how I'm using symmetry. I know that for every up, there's a down. For every right, there's a left. And that leaves me only, or so for every into of the page, there's an out of the page. For every up, there's a down. And that means the only terms I have to worry about are j-hat terms. All right. I'm going to pause there. It is my favorite time of the day, 5:55. So this is a good time. I'm going to see if there's any questions right now. I'll stop the live stream as well.